Good morning. Welcome back again. We're starting Lecture 3 today, or Chapter 3, with topic being igneous rocks. In fact, the next two lectures today and in the next lecture we'll cover igneous rocks. What we cover today will probably cover material that you're not that familiar with. Certainly on the next lecture, when we get into volcanoes, I'm sure this is what we see most often in the media about, or movie theater about, volcanic eruptions and people running from lava flows and explosions and so on. But today we're going to begin with the basics of that. But before I do that, I want to give you a reminder about the course itself a little bit, that again, it's helpful to have that pre-exam study term sheet with you to kind of follow along to see how we're doing, because that will be the main emphasis and focus that I use when I prepare the exams. Such that the way, if I give it through the PowerPoint or through you looking at it in the textbook, that gets you totally ready for that first exam. One of you asked me a question beforehand about when will the exams be. And the exams, of course, are listed on the syllabus, and times will be there, and I'll try to, in the classroom at least, remind you of that. If they're taking this from a distance situation, you'll have to depend upon the hard copy syllabus that's in Blackboard. So again, be sure to have that sheet with you. All right, the topic of igneous rocks. That's what we're going to get into today. Start out with some of the basics. This is a very unique spot in this picture, by the way. This happens to be out in California, called Devil's Postpile. As a geologist, I always wanted to get here, and I've yet to get there. Every time I head to California, I'm always in a different part of the state, or I'm getting close to this. It's a little more remote to get to the Devil's Postpile. But again, it's kind of unique. And again, I thought what I would do is show you some pictures of things that you may have seen in the news or in movies about igneous activity. This is what we see. This is a volcano, an active volcano that's erupting. This is Mount Etna in the Mediterranean, on one of the islands and countries in Mediterranean. You can see the big plume, the wind's transporting ash and dust and, of course, gases that are being erupted from that volcano. This is a very high-resolution satellite image of this, and that really helps geologists figure out what things are doing. Here's some uniqueness. I always wanted to see this live action of real hot red lava. I've yet to be to an active volcano that was erupting so I could see it. I was in Hawaii once, but nothing was happening, so I'll have to go back someday. But when you look at the character of this, you can certainly see the part that's melted. It's got a kind of a crust on the top of it. We'll talk about these lava flows and some of the things, characteristics about the nature of lava. I hope you never end up in a situation like this, being in a vehicle, driving extremely fast, trying to get away from an eruption of this nature. These are the types that are very, very damaging. You can die. Well, we'll talk about this type of volcanic activity again and look at this and see what happens. Sometimes you've got igneous things, igneous rocks around you. You've probably traveled across the country, maybe to in some national parks or some other areas. This is Crazy Horse Mountain up in the Dakotas. This happens to be a place where a gentleman by the name, he's not alive anymore, named Julkowski, an artist who's been trying to carve this huge granite mountain up here, and you can just begin to see the face and part of this. It's certainly advanced much more than it is now, but that's all igneous rock, a workable type of material. But to a totally different point of view, you've probably never seen something like this. You think, oh, I'm looking at a sponge close up under a microscope. Well, in a way, this spongy character here actually is a kind of lava. We call it golden light, and maybe I'll give you that name later on. You're not responsible to know. You can see it's full of holes. Gas oxide those, and of course when that liquid rock solidified, looking geometry to this particular stuff. And we'll look at why that is. Now this is a looking image. If you get an airplane, fly over a part of eastern Kansas in Riley County, north of Tuttle Creek Reservoir, and you look down and maybe about 500 feet in this plane. You look down, you see this circular kind of pockmark on the surface of the ground, and these little dark blobs are actually trees. Well, this is one of the rarer types of crops for igneous rocks in Kansas. So we'll look at some of the Kansas type of exposures. There's hardly any igneous rocks exposed at the surface in Kansas. We certainly don't have active volcanic activity out here. So as a geologist, it's unique to see that. And I'll show you what it's looked like. If you go down the central part of this, there's a little kind of intermittent dried creek that runs through here, and the rocks are exposed down in the bottom of that creek. I'll show you some of that later on today. But this is a typical picture of an igneous rock that shows its main type of character. When you look at these are individual crystals of different minerals that we've talked about now in this course. There are some quartz crystals in there, silicate, there are some feldspar crystals, maybe some hornblende, these different silicates we looked at here. But what's unique about it is it has this kind of crystalline look. It has kind of an interlocking nature to it. And it's got different colors in it. Well, we'll be talking about composition and texture and the nature of that as part of how we classify igneous rocks and give them names. What's unique about this one is that the central part of the picture has some pretty large crystals, and as you go to the margins, to the sides, the crystal sizes get what? Small. Why is that? We'll talk about what controls crystal size when we do that. So let's start taking a little bit about igneous rocks now. Where do they come from? Well, they form from magma, where the magma goes through a cooling process that solidifies it. So the terms cooling and solidification come into our vocabulary. Magma is simply liquid rock. Somewhere deep in the earth, we have situations where the rocks can get heated up enough to actually melt and become a liquid. And all those little bonds we talked about, we talked about chemical bonding, ionic bonding, covalent bonding, remember those? And when you heat them up, those bonds vibrate and move apart and break. And then atom floats off here and atom floats off there. That's called a liquid. And so as that liquid cools down in certain parts of the earth, at the surface of the earth, maybe just in the subsurface somewhere, those minerals begin to join up and bond again and create those silicate structures. So remember the term magma. It's liquid rock, and we refer to magma when it's under the surface of the earth. When magma comes out at the surface, we have another name. And I'll bring that up many times. It's called lava, and you probably are familiar with that. Okay, some other words to your vocabulary. Plutonic magma is the magma that stays inside the earth. So we have a term intrusive. Intrusive means it stays inside the earth. It intrudes into other rock zones inside the earth, and it cools and solidifies below the surface of the earth. That's a plutonic rock or intrusive conditions. Volcanic refers to the magma that comes to the surface, and we call it volcanic lava. This is extrusive because it kind of extrudes out of the earth onto the surface of the earth. Now, you know them as lava flows or other types of maybe violent volcanic eruptions you've seen in the news, large pyroclastic explosive pieces coming out, big bombs or material. We'll see lots of pictures of this in the next 2 lectures. So remember these 2 differences. Again, the interlocking crystalline nature. I've kind of abbreviated the word crystal by using XTALS. Okay? But if you look at this common igneous rock called granite, that's its official formal name, granite, you can actually see the crystal sizes. There are some large dark crystals, some light crystals. Some of them are almost clear looking. There's a mixture of those. Now notice the inset black rectangle. If we took that spot of the rock and cut it out and made it paper thin, in fact thinner than paper, 30 microns, very thin, and put it under a special microscope called a petrographic microscope, this is what we would see. Obviously the crystals get much larger, but we see a lot of detail in terms of the borders, the boundaries of the crystal grains. We notice that there's some color differences in these crystals. Well, in crystallography or in a class called petrology, geology students study this. They learn about the minerals and mineralogy. They look at these things under a microscope and they can say, oh, this is quartz, this is mica, this is a hornblende, this is this type of mineral. Because they learn what these things look like. And when you look at it, you can see some light areas and dark areas on the screen. If you actually take the place you put the thing on the slide on the microscope, that microscope stage rotates. And if you put in a special device, kind of polarizing lens, and when it rotates, everything changes color like a kaleidoscope. So it's kind of pretty to look at as well. But we also take advantage of that optical characteristic when we rotate the slide to help us identify minerals so we can classify the rocks. We want to know what's in that rock. It's not that we're just saying, well, it's pretty looking. We want to know what parts are there. Now, here's a totally different rock. All dark, completely dark, and you can hardly see any crystals. You can see a few white specks in here. But most of these crystals are very, very small, and it's difficult to see them with the naked eye. Under a microscope, you'll be able to see them, but this darker colored rock is referred to as basalt. Still has the interlocking nature, but the crystals are tinier. So why the differences? Why different colors? And why do we have different crystal sizes? We'll be leading up to that. Again, an inset, white this time. What does it look like under a microscope? Well, the crystals are much tinier. A lot of kind of lath-shaped or elongate crystals in there. Some are rounded, more what we say euhedral. And so there's a reason why that texture looks that way and what makes those minerals up. And now, what does it take to melt solid rock? What do we have to do? I think the first obvious thing to do is turn up the temperature. Increase the temperature. By doing that, the bonds vibrate, spread apart, and finally they break. Thing becomes a liquid. All the atoms move freely. Another thing to do is to decrease the pressure. Confining pressure, extreme pressure deep in the earth, pushes inward, pushes the bonds together so they don't pull apart. Even if the temperature is really hot and high above the melting points, they don't melt because the pressure is so high. It pushes towards the center of the crystal. So one way would be to decrease pressure. Another way you may not think about is if we can add water in some fashion, it's usually a water vapor form, this will help lower the melting points of those conditions, and so that helps break the bonds apart. So obviously, to solidify rock, what could you do? Drop the temperature, lower temperature, increase pressure, or what? Remove water. So this is to melt rock. To solidify rock, you just reverse these three. Where can we get the heat? Where does heat occur? What kind of heat sources do we have to cause this to happen? Now, most of us in here have not gone really deep in the earth. The deepest I ever went was in a mine down to about 2,400 feet under Minnesota. Took a big, long elevator ride all the way to the bottom, kind of wild ride, Mr. Toad's Wild Ride kind of thing, it's dropped really fast. And we get in there, and it warmed up quite a bit. Not a lot, but it warmed up. So as you go deeper and deeper and deeper into the earth, the temperature goes up. Get into some mines, like some deep gold mines in Africa, where they get down, a mile or two into the earth, and that temperature is really hot. In fact, they actually go to work in ovens. The elevators are ovens to acclimate to that temperature. And they work for an hour and then they get out because it's just too hot to work, and they have constant shifts going in and out of the mine. Well, this increase in temperature into the earth is called the geothermal gradient. It warms up. Of course, part of that heat, of why we have this internal heat, is a mixed bag of things, but predominantly it's the original heat of formation of the earth. When all the material came together through gravitational collapse, that friction that was created increased this heat. And of course, heat is dissipating, trying to come out through several ways, conduction and of course convection. One of these types of conduction or convective processes is where we have what we call hot mantle plumes. There are zones deep in the earth, maybe on the outside of the core, maybe in the middle of the mantle, maybe in the upper mantle where the heat is higher. And so because of that, what happens to air when you heat it up? Okay? It lowers the density, doesn't it? It expands. So you have a hot air balloon, so that mass of balloon rises. Same thing with solid rock. If it gets warm enough, it expands a little, that lowers its density, but extremely slow, that zone slowly rises to the surface. That's a plume, an upward motion of hot material. Later on we'll nickname them hot spots kind of thing. So these hot mantle plumes are rising, bringing this mass of material closer and closer to the surface of the earth. It's not a liquid yet. It's still under extreme pressure. Once that rising mantle plume gets close to the surface, the pressure drops, then what does it do? It melts. But not all of it melts. We'll get to that as well. Another major source for heat inside of the earth is where we have zones of higher radioactive minerals. Now, one of the byproducts of radioactive decay, as we know, is heat. We try to harness that for nuclear power. So again, some of the heat that's probably causing some of these hot mantle plumes is radioactive decay inside the earth. Later on, when we go into the interior of the earth, towards the end of the semester, we'll kind of come back to some of this, what we think it looks like inside. I'll have some computer models to show you. But those are the three main sources. All right, now to crystallize, what did I say earlier? Drop the temperature, cool the magma, increase the pressure this time, push inward, or what? Kind of get rid of that water, that steam, that vapor. Remove the water, so just the opposite. So this kind of listing little outline here would make a good type of multiple choice possible question, or maybe a true and false. I certainly will ask one or the other, maybe both, on the main exam. This kind of nice picture you see in the news a lot. Tough to pronounce that. Nyiragongo. This is in Central Africa by the East African Rift System. This was a volcano that erupted not too long ago geologically, maybe about 5 to 6 years ago, and came down and went right through a village. So you can see this lava oozing out in this picture. It's a nighttime picture, and you can see the flow moving in various directions, just like gravity, like a river. This is a river of rock, melted liquid magma. In this case, it's lava. But how fast can it move? Could you run away from it? Do you have to drive away from it? Well, one of the things you need to understand then and figure out about how fast it'll move is this idea of viscosity. So I want to talk about viscosity. If you've changed the oil in your car, you probably say, oh, I got 10W40 or I got 30 weight oil or 10 weight oil or whatever different weights. The higher the weight number, the what? The thicker, the stiffer that is. Well, think about liquid magma. If this lava is really, really runny, it'll move faster. If it's stiff, it moves slower. Well, this runniness and stiffness has to do with viscosity concept. And here's the definition of viscosity. It's one of these kind of double negative thoughts. Viscosity is a measure of resistance to flow. Key word there is resistance to flow. It does not want to flow. So if it has a high viscosity, as I show here a high V for viscosity, means it has what? High resistance. Means it doesn't want to flow, so it's stiffer. If it's a low viscosity, it means it's a low resistance, it'll flow easier. So we can kind of use a lay term of being runny or soupier or whatever. I suppose make some tomato soup or make some split pea soup to observe the differences of viscosity in soup. Okay? Now that's the definition of viscosity. I kind of want to look a little bit more at it. And before I do that, here's one of the towns near that volcano in Africa that I just showed you. Goma. Probably 8,000-10,000 people, I think, lived there. Now, is this lava flow moving fast? I don't think so. Not like in the movie, what was it, Volcano or L.A. or whenever they had that one? Moving that fast? Yes, they can move that fast, but this one's moving pretty slow. In fact, so slow they can pull up to some of the stores and get stuff out of it to save it. Of course, once the lava flow hits the wooden buildings, the buildings are going to burn. So reason why that's slow moving. So what controls this viscosity? We're going to look at a couple of parameters that control how runny or stiff this is. I think the most obvious one is temperature. The hotter you make it, the more you jack up the temperature, the more runny it will get. If you have a lower temperature, it's going to make it stiff. If it's a high temperature, it'll make it runny. So you lower the temperature, you have a higher viscosity. Now what does that mean? Let's go back to it again. It means it's stiffer. High viscosity means it has a higher resistance to want to move or flow. So you lower the temperature, it's going to be stiffer. If you increase the temperature, it's going to be what? Runnier. You'll have a lower viscosity. I didn't list both there, I just used one. Composition. Two things about the composition. The higher that silica content, the SiO2 part of the tetrahedron, the more little tetrahedrons you have in there, that means they'll begin to join up with each other. That will make that lava, that magma stiffer. So the higher the silica content, the SiO2, the higher the viscosity. That higher viscosity means stiffer. The second compositional kind of character deals with the gas. If you have less gas, again, it makes it stiffer. Higher viscosity. More gas will be lower viscosity and runnier. Now this is probably the more complicated part of this kind of looking at igneous rocks here, I think, than some parts. Especially because it's kind of a double, when you use the word resistance and you say it doesn't have resistance or it does have resistance, things getting higher and low. So just think about it and look at that definition several times. This would be something, again, I could put into a true and false type question. Probably one of the harder ones to remember. All right, textural terms. I showed you some pictures of crystals. Big crystals, little crystals. Sometimes we don't even get crystals. We just instantly freeze the liquid. We don't get crystal structure at all. There's a special name for that. You already know. We'll come to it. And this is it. You don't see any minerals in it. It's going to look glassy. So we use the term glassy. Glassy is the textural term that we apply to this. There's no minerals. We'll come to the reason of why that happens later on. It has to do with the rate of cooling. We'll come back to this again. If you have crystals, we say it has a crystalline texture. I'll give you some fancier names in just a moment. Some crystals are tiny, some crystals are big. If you look at a rock that has two different sizes of crystals in it, small and big, and various ranges of it, we have a fancy name. It's called porphyritic. That's kind of an adjective, and we say porphyry, that's a noun, but porphyritic means it's got large and small. And I'll try to show you some actual pictures of rocks that have this nature in just a bit. You can kind of rest your hands from writing. Is this pace going okay for note-taking? All right, good. That one I showed you all the gas bubbles in it, we call that vesicular. Kind of vesicular. Of course, most of the gas is released and goes into the atmosphere, or they might get dissolved in water. Sometimes minute parts can be trapped. Where you have a really eruptive, explosive type of volcano, like when Mount St. Helens blew, a lot of fragments are ejected rapidly out of the vent. That's called pyroclastic. Pyro kind of implying a fiery situation. We'll look at some different styles of pyroclastic material, probably more so in the next lecture. And lastly, sometimes you find some crystals that are really huge in an igneous situation. Not those selenite crystals I showed you last time, but in an igneous rock. Real large crystals. We have a special name for this. This is called pegmatitic. So again, there are more textural terms we have in geology. These are the main ones that we'll kind of introduce you to at this level. What I want to talk about are some of the other names related to this, and then why that happens, why we get these different textures, and then show you some pictures of them. Well, why we get these different crystal sizes and arrangements has to do with how fast the magma or the lava cools off. That's what creates this texture. Rate of cooling. So here's some terms for your vocabulary. If it cools instantly, we say it's glassy texture. Instantly is glassy texture. You probably know some rock types of volcanic glass. If you've been in some archaeology classes, obsidian. Obsidian is a volcanic glass, and I'll show you some pictures of that later. Now, if we just slow it down a little bit, so this is kind of a relative term. It's still cooling fast, but it's not instantly where it's frozen. This is fast cooling, and this fancy word up here, aphanitic, and you might want to put in parentheses after aphanitic, tiny crystals, very small crystals. In fact, you can only see them under a microscope. You can't see an aphanitic crystal by definition with your eyes. You have to use a microscope, so aphanitic. If we slow it down a little more, we'll just say slow, we got this term phaneritic. Phaneritic, you can see them with the naked eye. They're bigger, they're larger crystals. And porphyritic texture, what did porphyritic mean? 2 crystal sizes, right? 2 crystal sizes. So what kind of rates of cooling do you get in the history of this magma or lava if you got 2 different crystal sizes? 2 different cooling rates. Momentarily it's cooling down to this point, but the whole thing doesn't solidify, but maybe it's moved someplace and it cools faster. So you can get a mixture of fast, large and small crystals, glassy and small crystals in the same rock. It just depends on how those 2 different rates took place. So porphyritic are 2 cooling rates, remember that. And of course this explosiveness that's really fast produces a pyroclastic texture. So that's kind of a repeat or redundancy of the last slide, but we're looking at this from a point of view of how fast the liquid rock cools. And of course, very slow to a medium thing. We're slowing things down. The crystals have more time for the atoms to join. They get big. That's pegmatitic. Now, if I'm not mistaken, I think I have those PDF files out there that have all this already on there in case you're following along with some of this. I know that writing down helps. That's one of those things I told you about learning. Writing, seeing, and listening. Now let's take a break from note-taking and take a look at some pictures of some of this. On the top left, this black one is a special kind of volcanic glass you may have heard of as obsidian. Some of you may have heard about pumice more so. I know in lava soap they grind up pumice and ash and they'll put it in there. Pumice is very lightweight. It'll even float in water because it's full of what? Bubbles. It's vesicular, full of air. And of course, sometimes if it's just fragmentary little pieces of glass shards or fragments, it creates an ash like Mount St. Helens. First year I came to Kansas, 1980, the year I interviewed here, Mount St. Helens blew up. So the ash cloud was blown over and we went out in the parking lot and scooped some up with our fingers. It looked like fine dust on the cars. And you looked under a microscope and see little tiny fragments. Little fragments of glass like this. So here's different pictures of volcanic glass. The top left is a fragment just broken off like by a hammer or something. If you're into making arrowheads, they could use a deer antler and a leather thing to protect your hands. In fact, this stuff is so sharp, so clean edged, sometimes they used to use this, and in some places still use obsidian for surgery. Use it in eye surgery. It's a good cutter. Top left-hand picture is under a scanning electron microscope and it's been colorized. Bottom left shows some pumice floating, and then little pieces of ash in the bottom left, a scanning electron microscope. But it's all glass. None of this has minerals in it in these pictures. It's just solid, glassy material. the color bands in this obsidian in the top left have to do with chemical composition of that glassy material. Of course, look at these neat tools that we've made, humans have made. These are modern tools. You can go on the web and find websites to buy these. You can learn how to do this knapping process to make arrowheads and spear points and knives and so on. Or you can find them in the archaeology realm. Okay, quiz again, a little question. There's, how many grain sizes? 2. All the black matrix, which are little tiny crystals, too tiny to see with the naked eye, and those big white ones. Those are feldspar crystals kind of floating in this matrix of tiny crystals. So what's the name to the texture for that one? Starts with a P. It's porphyritic. Okay, a porphyritic texture. 2 rates of cooling created that rock. Underneath, it started cooling down, got big crystals forming, and then something happened. The magma chamber got squeezed, and the magma with these big crystals squirted out somewhere else where it was cooler, and the matrix cooled really, really fast. So we wound up with 2 different textures in the rock. So we've got composition, and we've got these textural things. This is what we use to classify igneous rocks. Are they dark colored? Are they light colored? And how fast did they cool? The color relates to the composition. The rate of cooling creates the texture. And I'm going to give you the names of the main ones that we look at. Don't forget this business of extrusive and intrusive. Extrusive is what? On the surface, this is lava or pyroclastic material. It's extruded on the surface. Now, a real common igneous rock that forms this way in a lot of lava flows is called basalt. That's its formal name. Basalt is a dark-colored rock. It's got, since it's extrusive, what do you think, because it comes out to the surface and would cool faster, what do you think the grain size would be? Probably tiny crystals, because it cools, kind of quickly. That's that fast one. That's aphanitic. Now, if that same magma, same composition, same stuff, stayed underneath where it was insulated inside the earth and it cooled down, the crystals will get what? Bigger, because it cools slower. It's the same mineral, same percentages, same color, same everything. The only difference is between these 2 rocks is what? Texture. Gabbro's got big minerals, basalt's got little crystals in it. That's it. Same composition. Now, if we start changing the composition around a little bit, though, and I'm going to throw you these next 2 up here in a row, let's jump to that bottom list. Leave a little blank in the middle and write the bottom 2 down. Rhyolite and granite. Okay, rhyolite and granite. Rhyolite and granite are lighter colored looking rocks. Why are they different color? They're made up of different minerals. But essentially, okay, they're lighter colored rocks and they're different minerals, but they're different than basalt and gabbro. Okay? Rhyolite and granite are made up of the same essential mineral composition. What's the difference? Texture. Extrusive and intrusive. If it's intrusive, it stays inside the earth. It's insulated, it cools slower. So it gets big crystals. So granite and gabbro are different compositionally, but they have the same, what? Big crystal size. They're both phaneritic. On the left-hand column, now this might be complicated, okay? The one on the left-hand column, basalt and rhyolite are different in color because they're made up of different minerals, but they're the same grain size. They're tiny crystals. And you don't need to worry about the ones in the middle in this class. I'm only concerned about kind of the opposite end differences and why we have it. It's color, okay? It's compositional differences, and texture is the rate of cooling. So here's some real examples of it. There's basalt and gabbro. They're darker colored. That particular gabbro is not as dark as the basalt is shown. But you can see larger crystals. The granite and rhyolite are lighter colored than the ones on top because they're made up of different minerals, different silicates, but they're different in texture size. Rhyolite's fine grain and granite's big crystals. And I'm going to see if I can get this little video going to let you watch to say, kind of where do we think these things form? In this cartoon, this animated movie that'll come up, we've got a rift system kind of right in here, okay, out in the ocean crust where this magma, this large hot plume is rising up. The pressure gets low right in here and drops, and so part of this is going to melt. part of this plume, partial melting, rises up, and you'll see little blips of lava squirting out in that crack as the seafloor forms. Where this plate moves away from that ridge and goes back down in the earth, that's called a subduction zone. And we'll get into more of that later on in this class. Watch what happens right in here when we start melting rock as we go deeper in the earth. And by the way, this ocean crust, what winds up on the top of ocean crust? Sediments plus what? Water. So you drag the sediments and water and that crust down in there. What was one way to melt rock? Add water. So by adding water in here, we can bring water in here, okay, and that helps lower the melting points. We get a lot of magma generated here. And you watch these little kind of like hot oil lamp blobs pop up and form these volcanic chains. Let's just quickly kind of run through this. You should be able, it's not very long, and you can kind of get this little animated idea of volcanic. We're going to look at this in more detail later on. Out there in the mid-ocean ridges, the volcanic activity is fairly calm, especially if it's deep down. It's under a lot of pressure. On the right-hand side, the mountain that you see in the volcanoes, some of those will be mellow and quiet. That depends on the composition of the magma. Generally, if magmas have more water, that's not good. It creates a stiffer magma, it's more pasty, and we get explosive eruptions like Mount St. Helens, Mount Pinatubo. We'll look at pictures of those volcanoes more so in the next lecture. So some of that magma makes it to surface, it's lava, it's extrusive. Some of these, though, right here on the right-hand side, these big blobs stay underground. They're intrusive. So we get granites, gabbros in here, and we get what? Rhyolites, and the other rocks coming out on the surface. Just composition, rate of cooling. Let's see if I can get this to move on here. All right. Now, what kind of shapes do we get? As these intrusive magmas develop, what kind of shapes are there? I'm going to give you some of the names that we have for them. There's going to be two groups to these plutons, two groups to the plutonic conditions. The first most new important word here is concordant. When magma intrudes in a concordant fashion, it squeezes in between the layers of the other rocks in the crust. The key word there is it goes between the layers. And I'll show you a real picture of this one. That's a concordant type of body. And we have several names to some of these shapes where they do this. Now, I'll give you two in here. The one on the left, like a windowsill, a flat horizontal layer, kind of thin, that's what's a sill. We refer to the flat, planar ones as a sill. They usually squeeze between sedimentary rock layers or between the layers in metamorphics. The word laccolith, again, it's a concordant. It squeezes between the layers, but the bottom stays flat and the top bulges upward, kind of makes a big curved upward mound on the top of it. And I'll show you some pictures of this one as well, a cartoon. There's a figure in your textbook that I'll be showing just a bit. So that's concordant. Just the opposite is where it cuts across the layers. Doesn't squeeze between, but cuts across. This is discordant. And there are three words here you have to see for this one. A narrow, kind of planar one that cuts across is referred to as a dike. And they're small in size and small in stature. But we start making them bigger and bigger and bigger, and they're kind of, huge magma chambers rising up through the crust of the earth and cutting across everything. The smallest of those two in the list is a stock. And I won't give you the size, numbers, and parameters. They're listed in the text, but I'm not going to make you memorize them. But the biggest one of all, like a bathtub, so to speak, is something we call a batholith. So a batholith is bigger than a stock, and both are bigger than the dike feature. So that's the terminology. Let's take a look at a picture that's in your textbook. Right here. Okay? Now, here we can see these layers that squeeze between. This is a sill. We're not going to talk about the stuff on top that extrudes. We're just looking at the intrusive stuff. These are our sills. So there's many flat-lying sills in here. The top of this one has somewhat of a bulged top to it. This is kind of a laccolith, but really to have a true laccolith, you need to have the layers above it bend. This one's not showing that. What's the one we call that cuts across? This is a discordant body here, another one over here. These other whole bunch of little ones that cut across the layers. What's the name for those small ones? Those are dikes. Now if they're small size and begin to cut across the layers, this would be a stock-like feature. And if they're real huge, that's a batholith. So they give you these cartoons in the book, and then we'll try to look at some real pictures of some of these. Now here's a real photograph. This central darker layer is a sill. That magma squeezed between the rock layer above it and the rock layer below it. This whole dark section is one huge intrusive concordant body. The real obvious one cuts across. There's a dike. And what's happening to the top right-hand corner, it just goes off the slide edge, is starting to what? Flatten out, almost be cutting between the layers like a sill. So they can be both from the same situation. If you ever have a chance to go out to Black Canyon of the Gunnison in Colorado, rather a unique place. You're driving along, the road comes to an abrupt end, and you look down in this deep canyon, several thousand feet deep. You can stand on the edge of one place, look 2,000 feet down. Looking on the wall in there, you can see all these lighter colored intrusions. So these are dikes, and some are sills. So it's a mixed bag. You can't see the country rock real well, the rock that surrounds it that it intruded into, but it's just shot through with these intrusive bodies. And of course, this is magma coming out outside of the earth, and a lot of these intrusive bodies have money associated with them. Gold and silver and platinum and molybdenum deposits are associated with this type of stuff. So we could dig into the mountains, in our mining areas out in Colorado and the Rocky Mountains. This is where we kind of follow those veins along, and then we process the ores. Oh, okay. I mentioned Kansas has igneous rocks. You need to remember for this class that most of the rocks at the surface of the earth in Kansas are not igneous. They're sedimentary. And we haven't even talked about sedimentary rocks yet, but rocks like shale, sandstone, maybe some limestones, okay? If you want to be able to see some igneous rocks in Kansas, you have to go out to several counties. Two main ones I'll point out. I have the big yellow stars there. The top star is in Riley County. The other one down the bottom right is Woodson County. All right? At some time in our geologic past, not too long ago, geologically speaking, magma was erupting and coming up through and towards the surface of the earth. Okay? And we can see some of this rock material still there. That circular picture I showed you was flying over the one here in Riley County. This is now down inside that circular depression. And this is that small stream that cuts through there, and this weird, ugly-looking rock. You go, oh, that's not unique. It's just like some blah rock. Well, if you're not a geologist, you might think that. But the rocks in here are kind of important because we have a fancy name for this style of rock out there called kimberlites. The rocks in Riley County, Kansas are kimberlites. Does anybody know anything about a kimberlite rock anywhere else in the world? From something that has a lot of value attached to it. You ever heard of Kimberley, South Africa? I showed you a really neat gemstone in the beginning. Diamonds. Diamond mines. When they first saw, they said, whoa, let's drill into this. Let's get a little deeper. Are there any diamonds in the Riley County kimberlites? No, apparently, according to the Kansas Geological Survey, there are not. But if there had been, that would have been an extremely valuable deposit, and that little ugly-looking spot could have made somebody very, very rich. So sometimes those igneous rocks have some unique value monetarily in economic deposits. So remember about that one in Riley County, that it's a kimberlite. It might have had diamonds, it doesn't, but it's an igneous rock. It's one of those examples. Here's a close-up of it, kind of unique. And what's really weird about this piece is that central dark area is a piece of the mantle that got ripped out as the magma was coming up through the upper mantle, ripping up through the crust and picking up other pieces of rock. And then as it finally cooled off, or before it cooled off, this magma, this lighter colored rock, was actually trying to melt and cause that central piece to react with it. And we got what we call a reaction rim. And a little bit of geochemistry there, stuff we could get into with some of the little weird garnets and other strange minerals. This is a very bizarre and unique rock. Right now it's not an economic deposit. Down in Woodson County, there's another rock that somebody's actually quarrying, though, and doing something with and making money. Near a place called Rose Dome. Actually, it's the microlite quarry. It's the same kind of similar rock. And what it is here's this goofy name, which I don't expect you to remember for this class, called a lamproite. But it's kind of like a basalt. It's a very dark-colored, heavy, magnesium and iron-rich rock. And deeper in the earth, it's real solid. Towards the top, it all got very chemically weathered and softer. And they can go in here and quarry that out. They bulldoze it out, put it in big piles and run it through a processing mill and bag it up and ship it out to places that make, this is what the rock looks like. The top right-hand corner, the bottom right-hand corner, same kind of rock, but it's soft. Very rich in magnesium. They grind it up into kind of a slurry or powder, and they make a special kind of vitamin pill with it, or they compress it into blocks. They give it to cattle. It's a vitamin pill because it's rich in magnesium. Here the cattle are kind of doing what? Geophagy, eating minerals, eating kind of clay-like stuff in there from this lamproite rock down in Woodson County. So even though we don't have the common rocks like granite per se and basalts, and here we got some weird ones, but they're unique. So yes, there are igneous rocks in Kansas. Ever get out to Yosemite? This happens to be a space shot of all the fires out there. On the left is San Francisco Bay, and here's part of the Sierra Nevada mountains. And right down in the bottom right-hand corner is where Yosemite National Park is. And if you go to Yosemite and drive on in, this is one of your first main views. You can see these kind of rounded, lighter colored rocks. You get down in the bottom of the canyon and look up and see these beautiful granite rocks. And they're everywhere. They're a huge expanse in the Sierra Nevadas. Well, these granites formed a big pluton underneath the surface. This is a batholith. The Sierra Nevadas are a batholith type of intrusion. Now, why do we see them at the surface of the earth? Well, because the mountains that were above them got eroded away. And that removed weight, and the crust rebounded back up. That's kind of what we call isostatic rebound, and brought those rocks closer and closer and closer to the surface. Now they are exposed at the surface. Kind of unique. So remember that Yosemite, the Sierra Nevadas, are batholithic structures. That's the key thing to remember. And the rock type, this lighter colored, coarse-grained rock, is granite. Closer to Kansas, in Colorado, in the south central part of Colorado, this is an infrared image over what we call the Rocky Mountains. These are the southern Rocky, the Sangre de Cristo mountain range. Over here is Alamosa, a great big valley down here. All those red dots are center pivot sprinklers, and so the vegetation shows up as red. And right here in the Sangre de Cristo, you've got these two little white blobs close by each other. These are the Spanish Peaks. They're beautiful. They're spectacular stock features that have now been exposed by erosion. And on a map, if you look at a kind of a tectonic map, from the central part of these mountains, these stocks are these radiating spokes like on a bicycle tire, bicycle wheel that spread out. And if you fly over the area, on the top right-hand and the bottom left-hand or bottom right-hand picture, you can see these real skinny ridges, straight up and down ridges. These are dikes. These are intrusive, discordant dikes. The central part of the mountain in the bottom left-hand picture, this is the western Spanish Peak, of course, is an intruded body of igneous rock. And it's a small in size, so we call it a stock. So what you need to remember about the Spanish Peaks? Stocks and dikes. Yosemite is what? Batholiths. Yosemite, batholiths. Spanish Peaks in Colorado, stocks and dike-like structures. Those are just a few. I could give you many, many more, but we're not going to do that. And here's kind of a unique picture. Quite pretty. It's a hot spring. This is a hot spring out in the northwest part of Wyoming in Yellowstone National Park. Extremely heated up water. Some of these hot springs, they have warning signs around. Don't fall in them, especially. You have to hold your children by the hand and don't let them get off because these waters will boil them. If they get in there too long, you can get killed falling in some of these. Others aren't quite as hot, and you can soak and relax yourself in some. Not in Yosemite National Park, but other areas around the country. Well, where is this hot water coming from? Well, it's coming from deep in the earth where groundwater percolates down through fractures and voids in the rock system and gets close to these magma chambers that are still cooling off. And that water gets superheated and it comes back to the surface. Now, if it's unimpeded, has a nice straight symmetrical path to the surface, it comes out as a hot spring. But if that hot water gets kind of trapped or finds some contorted asymmetrical pathway to the surface, it's superheated, it stays under there and gets hotter and hotter and actually goes above its melting point, or excuse me, boiling point. But it doesn't boil. It stays as superheated water. All right? But eventually it expands and you get towards the surface. I kind of imagine this is that there's a little burp of water that blows out of this hole. And you get a column of water that burps out, removes a big weight, a big column of water. What does that do to the pressure? Drops the pressure. So once you drop the pressure, it goes from superheated water to what? It just flashes to steam, and it comes blowing out of this asymmetrical and just ripping through the crust and spouts out. What do we call that? A geyser. You ever heard of what in Yellowstone? Called Old Faithful. So the symmetry of the underground plumbing system determines whether it's a spring or whether it's a geyser. This happens to be a hot spring. The superheated water is just full of minerals. Full of minerals that's dissolving from the rock under the surface. And so notice how the water's got a little steam on it. It's evaporating. So when you evaporate and get rid of the water, what happens to the minerals that are dissolved in it? They precipitate out. So see all that crusty yellow and other minerals along the edge of it? That's from the minerals precipitating out as the water evaporates or drains off the edge. The more yellow it is, the more sulfur that's present. The whiter it is, more usually silica or calcium carbonate type things. Different chemistries. And of course, pardon the bubbles. Obviously there's hot water, there's gas being emanated from these places. So we'll look at some of this dangerous stuff later on. I want to finish up more about what's going on with this superheated water though. Sometimes it's not just water, it's muck, slurried mud that's oozing out in these mud pots. Kind of unique. Top left is a geyser. Okay? That's Old Faithful. So sometimes they just steam vents hot water and springs all over the place. Bottom left-hand picture and the bottom right-hand picture are kind of these encrusted terraces. That's the minerals that precipitate out of this superheated water. Now again, the top left-hand picture, an Old Faithful, what happens is you get a little burp of water that removes the weight, that drops the pressure, and boom, then explodes out in that big steam vent that you see up there. And what happens? The old underground chamber gets empty. It's emptied out. So it stops. And groundwater percolates back down in the ground again, goes next to the magma chamber. What does it do? Reheats. So it kind of repeats the process. That's why it's faithful about every, what, hour or so, right? Now, if that underground plumbing system changes, it won't be as faithful. But this is superheated underground water. Well, if we could tap into this superheated stuff, pipe it out of the ground, and get it to convert to steam, and run it through some turbines, we can make what? Electricity. So we have this whole segment in the country and the world about geothermal power. Tapping into this superheated water. Where's it coming from? Most of it's coming from magma that's heating that groundwater system. The geothermal gradient can warm things. Some parts of the country you can tap into that and bring that through your housing system for cheap, free energy. But don't forget, in a geothermal power plant, this water is what? Very mineralized. So when you start running this mineralized water through metal turbine systems, some of that cool temperature of the metal is going to do what to the minerals in there? They're dissolved in there. They'll precipitate. So the blades in the turbine get encrusted with minerals and they got to change them out. Just like periodically you got to change your hot water system out. because it builds up and builds up unless you have a water softener and stuff like that. But so it's a way to have power and energy, but it doesn't provide a lot of energy for the world right now. It's not a major energy source, but we do tap into that geothermal power. It's certainly noisy. Anybody ever been by one of these plants? It's like listening to 747s take off constantly. So it's extremely noisy, and of course you have to spend the money to get your turbines, fans changed out quite a bit. But it's an igneous-related kind of process. So I thought I'd introduce it at this stage of the game. Are there any questions you have at all now about the stuff we've covered today? For the class here today, if you have any questions, go ahead and stay after class. If this is for the video, you can email me your questions or call me. So that's it for today.
It's mighty slim around here. Hardly no reward for a day's work.
Who turned that volume up? Okay, we'll see you next time. Take care.